All right, let's start with the class. Lecture number 6. I'm glad so many people actually made it, even with the snow. As you might know, I do record these lectures. They are all linked from the website, but don't take it for guaranteed that the videos will show up, because sometimes I have hardware problems, something crashes, and then there won't be a video. So most of them will be there for you as a reference. Next year it will probably be better because some of the videos are already there from the last year, but we will see. Hopefully it all works out. Okay, a couple of announcements. Homework 1.2, I think everybody has it done now. And you all should have submitted the files to circuit graphics. Hopefully we will be able to pick them up either the end of this week or early next week. I haven't really talked to them yet. These are just a couple of more notes when you later on do schematic designs. Some of them we talked already about. Top metal layer is not for text usually. That's what the top overlay or also silk screen is for. So silk screen is the actual name. Top overlay is what Altium calls it. Avoid direct pad connections on a chip. Now I have not seen it with any one of you. That might be because Enoch might have told you, but sometimes you see people, if the chip has 2 pads, they just connect them like this.
I didn't mention it.
You didn't mention it? All right, then nobody did the mistake. That's good. It's actually not, electrically again, it's not a mistake. You can do it, but it's just bad design. Because what will happen is, once you have the chip on top of here and you will solder it together, this will create a bridge between the 2 pads. Yet again, electrically it will work, but it will confuse you because you will look at it and think it's a short. Right? Unless you go back and think about the schematics again and you're like, oh yeah, no, these 2 pins are connected, it's actually okay. So usually what you want to do is you want to route out and then together here, not directly from pad to pad. Because it will just confuse you once you start looking at your designs again. You think there's a short there. And of course in this board too, the problem is many of these traces are not coming straight out of the track, also not nice to look at. Try to have them really perfectly nice out of the pad themselves. And here's a list of a couple of the DFM errors that you cannot ignore. So if it tells you anything about vias are too small, it usually means that you chose a drill size that's too small for the manufacturer. So if you would submit a board like that, they will use a bigger drill and just drill your pads right out, and you will have a short through these pads, or it won't be connected to your copper. Insufficient text width. Try not to ignore those either, because usually it means that they won't be able to print your silk screen. That your features are so small or so thin that they just won't show up at all. Signal distance problems can also, you can also not ignore. That's when your signals are too close to each other, so the traces are spaced too close to each other. Double drill hits, you should also not ignore. Most of the time the board house will actually fix them for you and just delete one of them. But it means that you have 2 holes that are on top of each other. So 2 drill hits are defined at the same location. If they don't correct for them, what can happen is that they drill in the same hole twice. And if they are slightly misaligned, it can be that the drill bit breaks and they won't be happy with you. Insufficient spacing is also one of these DFM errors that you can just not ignore, unless you really, really know what you're doing and this is okay with you. You might also have noticed that my voice today is a little bit raspy. I hope it will work out throughout the lecture, but if I have to cough and get something to drink, you know why. I have seen this in some of your assignments. Try not to do it. It's putting a via into a pad. What will happen is, if it's manufactured, it will look like this. And so the legs from your pads or pins will come over here, and this hole, once you solder it, will just suck all the solder away from the pad. And you might not have a connection there. Yes?
I did mention in my presentation how I screwed up 700 or so.
Yes,
pins.
we did. Because we did, not exactly like this, but something similar.
Same kind of thing.
So the problem with this is really like, this hole has a higher force for the solder to go to, and it will just suck it away, and your pad will not be connected. Even if it's sitting on there, it's a good chance that it won't connect to the metal itself. Now, that said, you can do vias in pads for very complicated designs. But usually what then the board house will do is you actually specify them as via in pads, and they will plug these things with metal. So they will actually fill them up with substance so that the solder doesn't go down inside the hole. So BGAs, for example, high-density chips, you sometimes have no other choice than putting the vias right into the pad where the via will, where the BGA pad will go to, because there's just no space under these pins anymore. But then they plug them all over, and that way you can actually do it. Any questions? Yes.
So with lab 2, the extra credit, how much exactly is the extra credit worth?
Again?
The extra credit on lab 2, how much is that worth?
Ah, I saw your announcement. I have to look at it again. I think it's probably like 5–10%.
Okay. Another question: if we do a different design because we're experimented, are you going to mark us down for that, or if it does basically the same?
In lab 2?
Yeah, for the LEDs.
Okay.
If we do a different design than just the one coming up, turn off, the next one going on, turn off. If we do something weird, just for fun, is that okay?
I think so, yeah.
Okay.
As long as it's more complicated than what's asked for.
Okay.
Yes?
Clarification on the light chase. Do the ones adjacent to the lit light need to be dimmed?
Ah, it does not have to be dim, but it would be nice if it would be dimming. So the idea was initially that you actually do the Night Rider. Like it's happening on the Night Rider. If you go and look online and search for Night Rider, it like has a light that goes back and forth, and actually it's not just one light that's going back and forth across it, it's actually the ones behind there like faded away. So if you can do that effect, that's perfect.
And I think a better reference for the current audience is to refer to it as a silent LED chase.
Yeah, that's a good idea. Yeah, definitely. That works too. Okay, one more thing. I know this was lab 1, but in case you have to measure some signal propagations again, signal propagations are measured from the 50% point to the 50% point. So it's not from bottom to bottom, it's not from top to peak, it's from the 50% transition to 50% transition. Okay? Another one is not completely wrong, but if you write Verilog and you have an output signal like this, that's a 4-bit signal, and later on you assign it as a 4-bit 110, it works, but it just looks weird. Right? Like try to really do a 0-110 or a 1-110. So you really know what's up there in that last bit. Okay, minute quiz. You know what? We had so many minute quizzes. I give this one as free for you. But get together in teams of 2. This is an important exercise. You have to be able to do and solve these kind of things for the midterm. All right? So get together in teams of 2. Try to solve it in, let's do 3 minutes.
We have to do this off the top of our head.
Sorry?
Off the top of our head?
Yes. Anybody done? Or has a good idea of what this should look like? So how many clock ticks will this take? 2? 3? So we have the whole thing. So we have 1 clock tick for the read address. Then, what do we say? 1 wait state, reading the data, and then what? What happens with the write, the read? So that was the write, now comes the read. The address is set up, so 1 more clock tick for the read itself, right? So it's 4 clock ticks that it should take. Make sense? So the first one, the first clock tick, oops. Let's do it this way. In this phase here, we set up everything with the adder. What's HWrite doing? High or low? High? So, high. HW data? What is it? Nothing yet. Exactly, we don't care yet. So, go through. HRead data? Nothing either. HReady? Up. Up. Right. So what's happening next in this clock tick? Address is becoming, staying. What happens? Staying. Next, it's pipeline, right? This becomes adder 2. HWrite. Sorry?
Goes down.
Down? Okay. HW data? Nothing yet. Read data? Nothing. Ready? Low, right? The wait state. Everybody clear why this is HAdder 2 now? Not HAdder again? Exactly. In the pipelining, he already moves on to the next one with HAdder. But then he tells him a wait state. So what does he have now? The master now have to do over here? Hold the address, exactly. So what happens here is we have the address, gets set in here, it gets changed in here, but held through the next clock cycle, etc., etc. You can finish the rest now. That's an important thing. Yes.
Your write data, where does it actually have to be set when you try to write?
This guy here.
Yeah.
It's a good, wait. Here. You're right. And then it gets held through this guy here. Because this one goes up. Good one. Okay. Yes?
So are these just flags saying that the data is somewhere else in the address array somewhere else, or are you actually sending the address bits to that signal?
Yeah.
Okay.
So that's this thing. HAdder is 32 traces that go from the core to each peripheral that everybody listens to. Now there is some matching stuff, and there's multiplexing in there too. There's multiple buses on top of each other. So it's a little bit more complicated, but you can think of it as the core has 32 lines, which is an address bus that goes out, and then everybody who's interested in has like lines on there to see if the address is for him or not.
Excuse me?
Yeah.
Why data comes one block after address?
Yes.
So the data,
Address, data.
but it's not ready.
Yes, but we write to it. What it means is when the peripheral tells you it's not ready yet, if you do a write, you have to keep the data there. And today we actually will see why sometimes this can happen. Like why you sometimes have to keep the data there. Because the peripheral probably has to do something in the background that needs this data constant throughout the transaction.
And read data come in the second clause. Read data.
Read data would come in here. So this would stay. This would come here. So it's after the falling edge. You can read the data. So the write data has to be ready before the falling edge. The read has to be ready from your peripheral. You have to provide it at the falling edge of the next clock tick.
But why it's not in previous clock?
Why it's not here?
Yeah.
Because the read was set up here, basically. So you have to keep the address here on the data bus, but because this transaction is still going on, this address becomes valid here, and then so the data comes here. You can't pipeline like a read and a write at the same time. Yeah. Because what would happen with this line here, where would this go high? I think it goes high here, if I'm not mistaken. Not entirely sure. Can somebody look up when H write transitions? Last lectures? Nobody has the slides?
I got it.
I can go to the next slide? That's right. So there's a transition, goes high. Yeah. Transitions here. Oh. Transition here. Not sure. Would have to look it up and think about it. Yes?
How many wires is in this bus here?
A lot.
What's like rough estimate?
Well, 32 plus 32 plus 32 plus at least 1, 1, and 1, so 3. And then there's a bunch of others, 8 tranche, just like 4 or 5, 6 and 7. Yes?
Why is the data, the read and write separate buses if there's only one address?
Because it's the AHB. It's not tri-stated. So you don't want to have any bus that has to be, one of them has to be tri-stated so that other people can actually use it. And so it's always like an output bus or an input bus. That's why they separate it. Because they want to make it high speed. Yes?
Sorry, I can't understand. The address 2 is
Yeah.
effective in that clock box. Okay.
You set it here.
Yeah. The next following edge we can have data.
No, because this line is low. You have a wait state on this transaction here. And that's why he has to wait with this address here for the next one and hold it constant. And then this is the read itself. Okay, last time we covered the AHB and the APB buses, and there are significantly different ways of how to use these buses compared to the external buses. So these internal buses, the 5-layer AHB bus matrix and the APB bus, they get used and accessed by using logic, so VHDL or Verilog. Now, in reality, once you use a microcontroller, you usually have no access to these buses because they are internal, they are inside of the chip. Peripherals use it to talk to the microcontroller, but usually you don't have access to these kind of buses. But in our particular case, where we have an FPGA, we actually have to use these buses, and you can generate these buses using your FPGA, because now you have the dynamic to actually write the peripheral by yourself. The external buses, that's usually what you have in microcontrollers and what you use to extend your embedded systems and hook up external components, like, for example, digital sensors, flash memories, and other types, SRAM memories, etc., etc. And these are accessed by physical wires. So remember, these internal buses, they're designed with logic. The external ones is where you actually hook up wires to a pad on your PC, on your chip to access them. So why not just export the AHB Lite and the APB? We had these questions last time, and I think he asked the exact right questions to tell you why this is not possible. Yeah. For the AHB, we would need almost 100 pins itself, right, to actually export it. Yes?
Do they on the Smart Fusion where it's got those gigantic
Mm-hmm.
ADR memory interface?
So they're not exporting it, no. But in theory, on the Smart Fusion, you could export the AHB bus. Because you have actually enough pads and enough I/O lines that you, in theory, could take the AHB and put it out on the bus. But the problem is, you won't find any kind of peripheral to hook up to it, because all of these things are written in Verilog. They get put into chips themselves. So it doesn't make much sense. Yes?
What's the motivation that we would want to export it off the chip again?
It's fast. It's really, really fast.
Wouldn't that be a longer distance though?
You would go over longer distances, yes, but it's still an extremely fast bus. If you could somehow manage to get it through the pads and outside of the chip. But the problem is it's so many wires, it becomes impractical.
I mean, it's faster if it's on the chip anyway, right?
Sorry?
It's going to be faster if it's still on the chip.
It will still be fast, yes.
Why would we want to do that?
Why would we want to do that?
Yeah, to export.
You could have an external memory or something like that hooked up to it. That would then be directly memory mapped I/O onto the AHB. And you will see why in a second, how we use memory, external memory, how it's slower than using the SRAM, for example. Okay? So let's talk quickly about asynchronous memory, which would be one of these things hooked up to one of these external buses. Yes?
Why the AHB supply here?
The AHB bus matrix, because it's a multi-master bus system, so you can have multiple masters using the bus at the same time, so you have to have multiple layers of how the routing basically can go.
Parallel here.
I'm not entirely sure what the implementation is, but if you're really interested in it, look in the Smart Fusion datasheet, and they talk about the AHB bus matrix and everything in detail, and how it's implemented and how you can use it. So let's talk about asynchronous memory. This is, for example, an external SRAM memory. It has 20-bit addresses, has 8-bit data bus, chip enable, write enable, and an output enable. Why would anybody use a chip like this? Why would you want to need external SRAM? How much memory do you have on your Smart Fusion?
512K.
256 or 512, depending on which version. And that's non-volatile memory. How much RAM do you have? 64K, right? So you don't really have that much memory on there. Imagine you want to make an MP3 player, right? You have 256K, that's not even a song where you can store in there. Nevertheless, you also need code somewhere, right? Or assume you want to run Linux on your microcontroller. Linux needs about 2 megabytes of storage. I think maybe a little less, maybe 1. Still, you couldn't run it on a microcontroller that only has 256K of flash. No less than 64K of RAM. So you need to extend your memory. This would be a solution of getting SRAM, fairly fast memory, into your microcontroller by hooking it up to one of your peripherals. So if you look at the definitions on these data sheets, you can see that the chip enable, output enable, and write enable will give all the different signals for reading and writing into your microcontroller. For example, if the chip enable is high, both of these states, the chip doesn't care what it is, the chip is not enabled. Once chip enable is low, output enable and write enable will tell what happens inside of your memory bank. So if output enable is low, write enable is high, you're going to read from the device. If write enable goes low, we don't care what the output enable is about, we're going to write into the device. And if both of them are high, the device goes into high Z mode. Yes?
So does this imply that writes have a priority over reads?
Yes. So what happens is you can actually make the model of this whole device fairly easily. You can imagine you have like an address input buffer over here. You have a row decoder and a column decoder for the address that you have. And then you have a squared memory over here. Using the row and the column decoder, you access a certain memory region inside of this memory bank. And you then have a control logic with the chip enable, write enable, and output enable that uses the I/O buffer to either push that data into your memory or take the data that's on here and push it out onto the data lines. Fairly simple. Yes?
Now, a device like this, you need a lot of pins to interface with, or you may cover this later. Is this something that you would only want to interface with a memory interface device?
Well, we will talk about that. So, if you look at the definition on here, there's no clock line, right? So how can you figure out how fast you can write into one of these devices? Or, for that matter, read from the device? Sorry?
Like, well, I don't know the actual speed, but since you're not using a clock, right? Some sort of handshake.
A handshake? Yeah, and how fast do you do the handshaking? Right? Can you go as fast as you want? Most likely not, because your memory array here has a certain latency to get the data out to your output buffers, or actually get it from the output buffers into the memory itself. And then if you go to the data sheet, you will see something like this, timing diagrams. So your device is completely asynchronous. This memory is asynchronous. But your device has a clock. So you have to manage your device and set the clock rates right in order to match the timing definitions of one of these chips. So let's look at a read cycle here. As you can see, what happens is the address has to be there. Chip enable gets pulled low. Remember, that's the only thing on how anything happens in this chip anyway. Then the output enable has to come after the chip enable happened. And then the data out comes sometimes later, defined by the TA and the TAC lines. And you can see there are multiple definitions for the same timing, right? So there is a limit on TAA, there is a limit on TAC. And sometimes they can be different. So sometimes you have to have the address on the bus earlier than the data actually comes out. Most of the times, these two times are actually the exact same thing. Okay. A write enable controls write cycle. What happens? Output enable, we don't care at all. Chip enable gets pulled low. Write enable has to be pulled low. And then there's a different timing that happens until the data has to be valid on the bus in order to be written into it. And there has to be a time the data has to be held stable in order for the chip to actually put this into the memory before you can actually turn it off. A chip enable controls write cycle. What happens is the chip enable gets pulled low after the write enable gets set. So there are two ways of actually doing it with different timing diagrams. Let's look at a different chip. This is an asynchronous NOR flash memory. Has up to 25-bit address bus. Can have a 16-bit data bus. So remember the one before had only 8 data. This now has 16-bit data. Chip enable, write enable, output enable, similar as before. It then has a byte interface, which can actually switch this chip between 8-bit mode and 16-bit mode. We have a write protect and a read busy signal, and you have a reset. The timing diagram looks slightly more complicated because now the outputs are high C, you have the reset line, the ready bit in this particular case, so this is a read cycle. Chip enable goes down, output enable goes down, write enable goes up, and the output becomes valid at some point. So now let's do an exercise. This is the data sheet for this particular chip. Let's try to figure out how fast we can read from this particular asynchronous memory. So I'm pulling this up here. What? All right. And we go one back. Getting groups of 2 together, try to figure out how fast you can read from this particular device. So go in, wait.
Lower 2.
There we go. Thank you. Confused myself here. Try to figure out, match the signals that are written in here, match them with the signals that you see over here, and figure out what you can do in order to read from this device. I wish I could. I can switch the two. Might that help? Okay, where do you start? What does your intuition as engineers tell you? Or computer scientists, I'm sorry. You start to look at this, right? So, what will tell you timing? Well, let's start simple. When can you start the next transaction on this device? Looking at this timing diagram. At the end, right? Like over here somewhere, right? So over here, the next one of these can start. Is this one here important, this timing? A reset? Not really. Not for maximum speed, because you're not going to go reset your chip all the time. That's usually high and just stays there. So it's somewhere over here that we start with a write enable. So we go a write enable, chip enable, output enable. It has to happen before these two lines can go high, this comes out, and then the data is down. Correct? Okay. How long is this time here? TCEH. Chip enable hold time, 35 nanoseconds. So the chip has to be enabled for at least 35 nanoseconds, right? It says minimum 35 nanoseconds before, from the write enable to here. Now, what's the next one? Sorry? How much is it? TCE? TCE is, well, oh, it says here. That's odd. It's different options, exactly. Different speed options. You can get them at 90 nanoseconds or very slow 130 nanoseconds. So let's take the 90 nanosecond one because we want to be fast. So it's 90 nanoseconds for this guy here. What about this? TACC. How long does that have to be? Also 90, exactly. So this has to be as long as this here, right? At the minimum. So we have 35, 90, and then what? What happens now? Sorry? TRC from TAC. Exactly, you have to hold the address for a certain amount of time. Is it TOH? No. That's when we close the whole thing down. Well, actually, at this point here, you're good to go. So you have to have a certain hold time here, TOH, output hold time from address chip enabled. Well, that's convenient. So this can basically be 0. So basically, as soon as this happens here, we are good. We're good to go. The data can be read And then we can break everything down. What about TDF? TDF, chip enabled to output high Z, 20 nanoseconds. Okay, so we add another 20 nanoseconds at the end. What gives that to us? Like the minimum fastest thing you could do with this chip.
145 nanoseconds.
Sorry?
145 nanoseconds.
145, so it's 90 plus 35 plus 20. All right, that's what kind of speed? So how many megabits per second would that be?
What's the width of the data bus on this guy?
Ah, good question.
It's 25.
You can do
25?
million transactions in a second.
So did everybody understand what the question is? No? Okay. The question is, how big is the data bus, right? We now figured out how fast we can read from it. But in order to calculate how much data we can put through, we need to know how big the data bus is. In this case, this chip can have either 8 or 16-bit data. In this particular case, we actually don't see it, so let's just say it's the full 16-bit to see what the maximum data rate could be. So it's 145. 110 megabytes or megabits.
Megabit. That's transactions times 16.
Times, okay. That will be
Oh,
megabit.
that is bits, right?
How much?
Divided by 2.
110 megabits per second. Is that much? Not so much? What do you guys think? 110 megabits per second. How fast is Ethernet? Depends on which one, but 100 megabit was actually fairly decent just a few years ago. These days it's gigabit. But so 110 is actually really not fast, right? Comparing to network connections. Turns out this is not a very fast flash chip. At the same time, this is also flash and not RAM. SRAM you could probably read a lot faster out than this flash chip here, per se. Any questions on how this worked? Yes, exactly.
Are there any considerations to be taken into account when we take the output value in terms of the device that's reading the flash chip, how long it would take? So would that increase that output?
Most likely. What we did is the calculation that could be the maximum to read out this chip. Yes?
How did we get 110 megabits?
We took the time it takes from here to here. One divided by that gives you the frequency, and then multiplied by the width of the data bus. That gives you the number in bits per second. Yeah?
Are there different trade-offs when you choose your speed options, like the slower, like less power or something?
It's usually price. Yeah. The faster they go, the more expensive they become. Because how they do it, they probably produce all of them at the same mass, they're the same chips, and then they sort them. So the ones that are slower, they become cheaper, and the ones that are faster, they charge you more for. Yes?
Also looks like this chip can go slower at the sacrifice of supply.
Looks like it. Yes. So if you look at the setup here, ECE 2.7, they're only available, or they're going in slower speeds. If you go actually with the fastest one, you need 3-volt supply voltage. You can't go lower in voltage. Good mark. So assume you had this chip. How could you go faster than 110 megabits? But this is the only chip I give you. What could you do? Yes. You can have them in parallel. Let's look at this in a second on how we could actually improve that. All right. Yes?
Give me, tell me repeat again how to calculate this duration. This duration is 90 plus 20 only?
No. It was the setup here in the beginning, which was the 35. Then we looked at a couple of signals here, but it turns out they don't really matter because several of them are 0 nanoseconds, so you don't need any setup. The longest one was then this guy here, which has to be 90 nanoseconds. And then you had a hold at the end, which was another 35 seconds, nanoseconds. So it's 90 plus 20 plus 35. Yeah?
it also, so this chip won't, you have to address every single read, right? You can't do burst reads or burst writes if you wanted to.
Could
That-
be.
That would speed up too.
It could be. So sometimes you can, if you tell the chip that I want to read starting from this address for that many bytes, or just keep reading, it will just keep incrementing and spitting out the data, and that sometimes can go a lot faster. But I'm not sure if this particular chip has burst modes. It might. Okay. Another nice part about memory controller interfaces is that you don't really need the memory on the outside. For example, in this particular case, we have an LCD controller that mimics a memory device. So it looks like as if it were memory, and you can hook it up to a high-speed memory interface, but instead of writing into a memory, you're actually writing into the LCD controller's registers, and that way you can update or refresh an LCD extremely fast using a memory interface. So in this case here, this is actually the memory controller chip, the LED that you have on the Smart Fusion, which is a 96 by 16 OLED panel that has a memory interface or an I2C interface. And I think in your case, on the Smart Fusion, it's hooked up as an I2C device, not as a memory interface. But the same device could be used either through I2C serial, which we will talk about later, or through this particular memory interface. Okay, now comes the question, so how do we hook up such a memory into our Smart Fusion? Or for that particular case, in any kind of microcontroller. And usually what you have is an external memory controller, or EMC. There are lots of different bus systems out there. You probably have heard about ISA, VESA, AGP, PCI, DMI, IDE, CF. They're all different definitions for slightly different types of devices. Microcontrollers often have integrated external memory controllers that can mimic different types of memories and that can talk to different types of memories by configuring them appropriately. In our case, the EMC on the Smart Fusion has a memory location starting at 7000 and goes up to 77FFFFF. That's a lot of memory, right, that we can address. How much is it? How much memory can we address? Anybody have a calculator? Because I don't have it in my notes here either. How much? 2 by 10 bytes? 2 to the 10? That would be only a K, 1 kilobyte. This must be a lot more than that. 2 to the 26, that sounds more like it. How much is that?
67
Megabyte? So 64 megabytes. We can address 64 megabytes of external memory through the EMC, which is really neat. And as you can see, it's actually mapped into your memory space. So by you just going and reading that memory location, it will actually go outside of your chip into the memory, read it from there, and give it back to you on your AHB bus as if it were just flash storage, as long as you configure your EMC appropriately. So the EMC now offers an external interface of 2 different chip selects. It has 8 or 16-bit shared data bus, so you can configure it what you want to use. It can generate write enables, can translate the 32-bit AHB transfers into half-word and byte transfers. So you actually don't care on the core if you read from the EMC. You just read 32 bytes and it will actually generate the right transactions on the outside, either 16 half-words or byte transfers. And it can also automatically align misaligned addresses. So if you do a mistake in your read and write, it will actually align them appropriately for you in how to do it. This is the interface definition. What you can see here is the AHB interface up here. Down here you have the control itself of the whole EMC and how to configure the EMC. It sits at a different memory location where you set up all your configurations for it. And then you hook it up through an I/O bank to your external memory device, or EMD. Makes sense so far? Yeah? Maybe? Not really? So what happens? You're going to read from the AHB, right? You can have a read transaction on your AHB on here, somewhere within the 7,000 memory range that we saw just before. the EMC takes that read and translates it into an external memory interface definition. Now we just heard they are significantly different, right? Like you can over here you can have 32-bit data reads, while this interface here can only have 8 or 16-bit transfers. So the EMC actually takes care of these kind of things and necessarily generates multiple reads and writes from out here from this device to present and give you an answer on the EMC. So just a quick rehash. We have a read transaction and a write transaction, right? Pipelined, extremely fast. Now if we add the EMC in there, it's not very fast anymore. Because all of a sudden you have to talk to an external device. Sometimes you have to do multiple reads and writes from it. So what the EMC has to do is it has to add wait states into your transactions. So all of a sudden your AHP that was super fast becomes slightly slower. But at the convenience of extreme easy use for you, you just read and write memory locations, the EMC does the rest. So what would happen is, for example, the AHP would have a read transfer with wait states, similar to what we had here before. It sets up the address, wants to do the next one, but it has to wait because the EMC says, hey, wait, I have to do a transaction off chip. You need to wait until you get your data over here. This is a more in-detail example of how this would work, how the EMC actually does this particular operation. In this case, we have the AHP, the EMC uses an extra cycle for the EMC to actually set up everything on the outside. So that's up here is the AHP, this is the EMD interface. We have the address phase, so the EMC now knows something is going to happen. It will set up the address on the outside. And in the next cycle, it tells you, okay, we need to wait. It will do the chip select for the outside chip. It will do an output enable. We'll get the read from here and then push this out onto the data bus later on. So this data that got right here will use one extra cycle to appear on the AHP. It's not very efficient use of the AHP because all of a sudden, if you just do one read from it, you have to wait, instead of just having it in the next clock cycle, you have to wait for 1, 2, 3, 4 clock cycles. And depending on what type of chip you have out there, this might be even longer, depending on how fast you actually can read and write to it. Any questions on this? How the translation works? From the AHP into the external memory interface and back? No? Okay. So how does it do all this translation stuff? Right? You have a lot of virtual memory or memory locations for the EMC that somehow get mapped into a chip on the outside. So here is a case for when we do a 32-bit read on the AHP bus. What's actually happening is that it gets translated into multiple reads or writes, depending on what you do, in your memory location on your chip. And the addresses really get just translated over into the other space. So if you have one address space going from 7000 over here to 77FFF, what happens is that this address 0 gets actually mapped to its address 0 on the outside chip. For the second chip select, you go from 74 up to 77FFF. Right. This should be a 3 over here. This is a mistake. So you have two chip selects for two 64 megabytes spaces. They get mapped to two different chip selects. So if you have two different chips, they get start at the bottom and just go up in byte order. So before we asked, so how can you go faster or have a faster chip? Well, you can have chips in parallel. If you use, for example, a byte type device, you can hook up both of them in parallel, but choose the two addresses differently. So the last bit has to be different on the addresses. In addition to that, you can have them share the data bus. So what you do is you have one chip is hooked up to 0 to 7 on the data bus. The other chip, you hook it up to 8 to 15 on the data bus. And now the address, if you actually look at it, the 0 bit gets dropped. This one has address 1 to 250 and 1 to 250. Bit 0 is not even connected at all. And now if you actually address and write into it, and you control your EMC and tell him that this is actually one chip that has a 16-bit data interface, the right thing will happen. What happens is the following. Bit 0 will be put onto the lower one. Byte 2 will be put in this one. The next one will be put in this one. This byte will be put in the one up there. Right? So the EMC takes care of the mapping between your memory, your AHP, on how you address it, and how it's distributed out on your memory chips outside. Sometimes you can play some interesting tricks. So pushing this one further, pushing this one further, you can actually have, since we have two different chip selects, you can have two chips up here and two chips down here, both sharing a byte interface, but interfacing them into the same memory location. A different example, you don't have to just be asynchronous. The EMC also can generate your clock in case you have a synchronous device. In this case, the EMC gives you a clock into your chip outside, and then you have yet again a different memory interface. So the EMC is extremely versatile. All you have to do is actually figure out how to configure it right, set up the timings right and appropriately for your external memory chip, and once you have it set up correctly, it's really easy to use from your code. Right? In your C code, all you do is you just make a pointer, point it into the EMC address, or have an array or something like that, and then you start reading and writing from it. The EMC will do the rest of storing it out there or reading from it. Yes?
Would you define something like this in the linker script, where you'd say, I have this much memory,
No.
and now I have even more here?
It's probably in the boot up of your device.
So you couldn't tell C to extend the size of the stack by saying, you have memory at this location and memory at these locations.
You probably could, but you have to make sure that the EMC is set up before you start using that stack up there.
Could you?
So yes, actually, no, yes, you're right. You could put code into these memory locations.
Well, not just code, but have C treat it like the stack.
You could, yeah, you probably can put the stack up there.
But you have to set aside C.
But you have to configure this EMC before you move the stack pointer up there. Yes.
Well, you can do that. You can have startup code. And
Yeah, I'm not saying you could not, but you just have to take care of it and see. Okay, open discussions. Any questions? Questions on labs? Questions on the homework? Anything?